Good morning, students. In the previous class, we were discussing these two load lines. One is DC load line and one more is AC load line. Just to have a brief revision, DC load line is with respect to the DC equivalent circuit and AC load line is with respect to the AC equivalent circuit. You are quite familiar with the DC load line. You can see the picture also that is on the screen. This is a regular voltage divider bias amplifier, and when the transistor is completely in the cutoff region, the voltage at the collector will be VCC, and that is at the x-axis. At that time, IC is going to be 0, and when the transistor is completely in the saturation region, the voltage across the transistor will be 0, VCE will be 0, but the current there will be IC sat. How to calculate IC sat now? Saturation current, that is when the transistor is completely on, that is simply VCC divided by RC plus RE, because this switch is completely closed. So that is how you can see in the y-axis a point corresponding to VCC divided by RC plus RE, that is IC sat, and at the x-axis you can see VCC. Now when we join these 2 points, then that is load line, and the midpoint of the load line is generally the ideal quiescent point. We can write the AC load line also with respect to the AC equivalent circuit. We have already seen how to write the AC equivalent circuit in the first module itself, while calculating the gain and input impedance and output impedance using the RE model and later on using the hybrid model. So let us see now how to write the AC equivalent circuit also and how to plot the AC load line also, but the Q point is the same with both of them. Now you may think, why we require these two load lines? Why we require an AC load line now when we already have a DC load line? The point here is, with respect to power amplifiers, we will not get exactly whatever we expect at times, because power amplifiers are also called as large signal amplifiers. In the case of small signal amplifiers, we will be working only around this Q point. We will not be exceeding the limits here around the Q point. But with the power amplifier, the Q point can be shifted to some other place depending upon the input signal's amplitude. In the sense, even if the Q point is not shifted, the switching of the transistor will be to the two extremes, to the cutoff as well as to the saturation. Actually, we are using this amplifier for AC power only, so naturally it is a good idea to plot a load line with respect to AC circuit also. But then how do we say the Q point is the same with both of them? Because the Q point is the one which we are setting, and these two lines will be intersecting there. I will show you that in the next slide. Now proceeding with this, we know that IC sat is equal to VCC divided by RC plus RE, and we also know that VCE cutoff is equal to VCC. So these are the 2 points at which we join them and we obtain the DC load line. Obviously, when IC sat is there, VCE is 0, and whenever VCE cutoff is equal to VCC, IC itself is 0. So that is how we join these 2 points and obtain the DC load line. Let us see the AC load line now. Now in this slide you can see the AC equivalent circuit. The same voltage divider bias circuit, when it is plotted with respect to AC ground, we can see that R1 and R2 are in parallel here at the input, and there is one small RC connected to ground from the collector. That small RC correspond to capital RC parallel with RO. Let me show you here. We have this capital RC and we have this RL also. If RL is connected and we have this RO also across the collector junction. Anyhow, emitter is connected to AC ground. So that way, that small RC can be written as capital RC parallel with capital small r naught parallel with RL. If RL is connected, if RL is not there, then it is capital RC parallel with small r naught. We have seen this earlier. So that is represented with small rc here. Now, with respect to this, we can plot AC load line. You can see on the screen, there is an AC load line here, and you can see for the AC load line, there are 2 points corresponding to IC sat equals ICQ plus VCEQ divided by small rc. This is slightly different from the DC load line's corresponding point. Similarly, you can see there is a small error here. VCC is supposed to be to the right side. VC cutoff is supposed to be to the left side. This VCEQ plus ICQ RC is supposed to be to the left side. But anyhow, it is VC cutoff corresponding to both of them. So, this point is corresponding to VCC. And this point is corresponding to IC sat. That is VCC divided by RC plus RE. Because this line is the DC load line. Whereas, this line is the AC load line. In this AC load line, you can see the x coordinate is VCEQ plus ICQ into RC, and y coordinate is ICQ plus VCEQ divided by small rc. As I told you, these two have to be interchanged. This VCEQ plus ICQ RC should come to the left side, VCC should come to the right side. So there is an error even in the textbook when they printed this picture, but that is only a typo error or an editing error. So we only have to correct it when we analyze it. Fine. Now let us see how we get the points corresponding to the AC load line. From this equivalent circuit, we can write that small VCE plus small IC RC equals 0. Why? As per this equivalent circuit with the AC, applying KVL at the output loop. Let me annotate now. When we apply KVL at the output loop, we know VCE plus ICRC equals 0 in the AC domain, because this is with respect to AC equivalent circuit. That is why you can see all these terms are in the smaller case or lower case, not in the upper case. So small VCE plus small IC into small RC is equal to 0. So now, using this expression itself, we can write small IC is equal to minus of small VCE divided by small RC. This RC is nothing but the dynamic resistance at the collector or AC resistance at the collector, which is nothing but the parallel combination of capital RC along with the small r naught along with capital RL if it is present. So we can write small IC or the AC current is equal to minus of VCE divided by RC. Now IC is what? In the case of the AC load line, small IC is what? Delta of capital IC. What was that capital IC? Capital IC was the DC collector current. Now the small IC is nothing but the change in that DC collector current when the input signal is applied. Whenever an input signal is applied, the transistor will gradually move between cutoff and saturation. So there is a change in the quiescent current as well. Current will not remain the same. You can see this picture here where input is applied and the output is obtained with respect to Q. And you can see with respect to that, there is no distortion at the output. Now, that is plotted with respect to AC load line, not with respect to DC load line, even though the Q point is the same for both of them. So, small IC is the change in the DC current, that is what? IC minus ICQ. ICQ is the quiescent current and IC is the changing current now. So that way IC minus ICQ is small IC, that is the change in the quiescent current. Now, what is small VCE? Small VCE is the change in capital VCE. Earlier VCE was ideally supposed to be VCC by 2 with respect to DC load line. Now, when we apply AC signal at the input, even that collector to emitter voltage is going to change. Now, that delta VCE is nothing but capital VCE minus VCEQ, where VCEQ was the quiescent point and VCE is the changing value. Now, with respect to this, we can plot the DC load line now. Rearranging and substituting the terms accordingly, the equation for the AC load line is obtained now as capital IC is equal to ICQ plus VCEQ divided by RC minus VCE divided by RC by using these two equations. We have the upper equations here. Small IC is equal to minus VCE by RC. Now we can use this along with this. And we already have an expression for small VCE. We can use this equation along with this equation and we can rearrange for obtain an expression for capital IC, that is the current at the collector, and that is nothing but ICQ plus VCEQ divided by RC. You can see that here ICQ and VCEQ are already there with the DC load line itself. Now minus VCE by RC. Here IC and VCE are going to change with respect to the input signal. So the endpoints of the AC load line are what now? IC sat is equal to ICQ plus VCQ by RC. How we obtained this IC sat? That is because when a transistor saturates, then VCE is going to be 0, right? If the switch is completely on, then the VCE is going to be 0. So now IC sat is equal to, because this VCE is 0, ICQ plus VCQ divided by RC, only the first two terms in the RHS of the equation. Now, what about VCE cutoff? When the transistor is in the cutoff region, there will be no current at all across it, right? So IC itself will be 0. So we can use the same expression which is at the top and we can rearrange for getting this VCE cutoff now. So using this equation, VCE cutoff is obtained as VCEQ plus ICQ into RC. Using the same equation, in this case, you have to make IC equal 0 because when the transistor is in cutoff region, current across it is 0. So when you make this 0, the whole equation becomes equivalent to 0. Then rearrange the terms in such a way that you will get here at the denominator RC is there. Here also at the denominator RC is there. So naturally that RC gets cross multiplied to ICQ. So we can find out anyhow this minus sign when it goes to the left side it becomes plus sign. So we can write VCE cutoff equals VCEQ plus ICQ into RC, which means we have obtained 2 points now which are corresponding to the AC load line. With respect to AC signal, when the transistor saturates, you can see the point corresponds to ICQ plus VCQ divided by RC, and when the transistor is in the cutoff region with respect to AC signal, we can see that VCE cutoff is equal to VCEQ plus ICQ into RC. Now using these two expressions, we can mark the AC load line. That was what I showed you here. Using these two expressions, you can say IC sat is equal to ICQ plus VCEQ by RC. That is what is this. Then the second one is VCE cutoff is equal to VCEQ plus ICQ into RC. That is what is this. Actually, this corresponds to this point. Okay. I had told you already, this is an error which is there in the textbook itself. But I am telling you that you should take it in the other way. Okay. So now using these points, we will plot the AC load line. Now from the DC equivalent circuit, the equation for the DC load line is obtained already. This we are already sure that ICQ is equal to VCC minus VCEQ divided by RC plus RE. The quiescent current in the DC operating conditions is total voltage is VCC and there is a VCEQ across the transistor. So ICQ is equal to VCC minus VCQ divided by RC plus RE. You are already familiar with this particular expression now. So AC load line has a higher slope than the DC load line. When you compare these, we can compare here itself. You can see the AC load line has a larger slope than the DC load line, which means in the case of AC load line, the maximum voltage at the output will be less than VCC. Actually, this corresponds to VCC and this corresponds to VCEQ plus ICQ into RC. So you can see with respect to AC load line, the maximum voltage at the output will be less than VCC. Even though we presume that the Q point is at the middle of the load line, and we presume that there is 50% space at the top side as well as the bottom side with respect to DC. But with respect to AC, it is not so, because of the AC equivalent circuits analysis. And with respect to DC load line, we had this IC sat, but we can see with respect to AC, the IC sat is also larger than VCC by RC plus RE. Now, how current became larger in the case of AC load line? When current can be maximum here at this point, where it can be maximum VCC by RC plus RE, how can current increase at the output with respect to AC? The reason is input signal is also contributing current. We are discussing the power amplifiers. And now the input signals are not small signals, they are large signals. Input signals also have got enough power now. When they got enough power, there is this base current which is predominant now. Unlike the earlier case. In the earlier case, at many points, when we used to analyze the circuits, we used to ignore the base current with respect to the collector current. Now in case of power amplifiers, base current cannot be ignored with respect to the collector current. So that is how you can see there is an increase in the saturation current. When there is an increase in the saturation current, naturally there is a decrease at the output voltage in the cutoff region, because the load line is anyhow going to be a straight line there. So that way AC load line has a larger slope now. So we will have to analyze power amplifiers with respect to AC load line only, and DC load line was meant for only fixing the quiescent point, that's all. Quiescent point is going to be the same for both load lines. But as far as the output amplitude is concerned, DC load line is not of any importance now. That is the point. You can see there is this Q point, there is this DC load line, there is this AC load line, and you can see this is an unfaithful amplification. See, when the input signal is let us say much larger, with respect to AC load line only we will have to get the output now, because as the saturation current with respect to AC load line is more, in the x-axis the voltage when the transistor is off is going to be less now, because it is going to be a straight line now, due to which now you can see the full signal is not available at the output. In the earlier case, we could presume that the signal could go up to VCC also. Now here, it cannot go beyond this VCE cutoff with respect to AC load line here. So, but at the negative cycle you can see it can go up to 0. At the positive cycle it cannot go up to VCC. Now this is an unfaithful amplification, which means we cannot apply an input signal which is much larger now for this amplifier, because we are dealing with a large signal amplification now, right? We are not dealing with a small signal amplification. In the case of small signal amplifiers, we used to presume that the input signal will be only around the Q point. But in the case of a large signal amplification, the input signal can be much larger. It can be having a larger swing with respect to the Q point. Now you can see this is an unfaithful amplification here. Now how should be the faithful amplification? Now this is a faithful amplification, where you can see AC load line and DC load line are having the same slope, but input signal has to be applied lesser only now. You can see here. Here, with respect to this, when the input signal was here, we had unfaithful amplification. You can compare the right hand side's picture with the left hand side's picture, and you can observe that the Q point is shifted. Even though the slope of the load line is same, Q point itself is shifted. You can see here. Here the Q point was somewhere at 6 volts. Now here the Q point is somewhere at 4 volts. So that is the measure which we have to take. That means in the case of power amplifiers, both load lines have to be plotted, and we will have to fix the Q point in such a way that again they intersect. You can see here. Here also they intersect. But we fix the Q point. When we fix the Q point with the DC load line itself at a different position, when we plot the AC load line again, anyhow that is going to be coinciding, because Q point for both of them is going to be the same. Why? Because ICQ and VCEQ are utilized in both the expressions, right? You can see here. Let me show you the previous slide again. You can see here, ICQ is also there, VCEQ is also there here. Here also ICQ is also there, VCEQ is also there. That means AC load line essentially contains DC load line's quiescent point only. That is why I have been telling you that Q points is the same for both of them. Now, in order to have a faithful amplification, we should fix the Q point carefully here. Now, you can see here also input signal was from 0 volts till 6 volts. But at the positive cycle, there was an unfaithful amplification. Now, when we shift this Q point to the left side, we have this input signal from 0 to 4 volts. But somehow we are having a faithful amplification here. Now you can see here, totally the peak to peak is remaining the same. You can see here, the peak to peak amplitude of the output signal in the both cases is going to be same. That means the input signal's amplitude has to be lesser in both cases. Only thing is, we are getting a faithful amplification when we shift the Q point. So, this is the care which we have to take when we design power amplifiers or large signal amplifiers. Now, the maximum peak output is what? Maximum peak output is ICQ into small RC. Because with the AC load line also the term ICQ is there, quiescent current is there. So, quiescent current into that AC resistance at the collector. Either that or VCEQ, whichever is smaller. Please remember this. Whichever is smaller. Why? Because the AC load line's slope is different from the DC load line, and you can see we are having a limitation for the output amplitude. So, the peak output MP, maximum peak, is either ICQ into RC or VCEQ, whichever is smaller. Therefore, MPP, maximum peak to peak output, is going to be 2 into MP, 2 into maximum peak output. We are going to see this when we work out the exercises in the next slides. But remember these expressions. Maximum peak can be ICQ into RC or VCQ, whichever is smaller. How to correspond it to this graph now? You can see here VCEQ was around 6 volts. Here the VCEQ is around 4 volts. Now if ICQ into RC is larger, then in that case, in the second case when we have faithful amplification, the maximum peak to peak can be only 8 volts. You can see it here, right? 0 to 4 and again 4 to 8. So this can be maximum peak to peak value at the output. We can get only up to 8 volts, even though VCC is 12 volts. You can see here, the VCC is 12 volts. Even though VCC is 12 volts, we can get an AC output of maximum only up to 8 volts. That is the limitation of large signal amplifiers. Okay, let me proceed to the next slide. We will have an exercise now. Now you can see two people exercising just for a fun or a humor in the class. Sometimes class can be boring when I keep on speaking in my own way. Just to have a humor, I am putting some pictures here. That's all, nothing else. Now, because it is an exercise, I put the picture of two people doing exercise. One person is trying to do an exercise on a machine, and the other person is trying to touch his own feet, which is very difficult for him. Somehow they have to reduce their weight. In your case also, now you are quite young. When you cross middle age, you should take care of not to become overweight at all. For that matter, even now also you should take care not to become overweight, because gaining weight is very easy. Losing weight is very difficult later on. You can see how people work a lot to reduce the weight, and how there are many marketing therapies also available for losing weight. That becomes very difficult when we gain the weight to lose the weight. And heavy weight itself is one of the reasons for loss of health in future. So this is my health tip. Even though it is in the technical class, at times I give such tips to students thinking that it will be useful to you in your life. So never become overweight. Keep on exercising so that you'll be fit and fine. You keep yourself warm always. Once the body remains warm, naturally germs will not multiply inside the body. Germs will multiply only when there is a optimum temperature for their multiplication. If the temperature is more, germs cannot survive. That is the secret of health. Okay, now let us proceed to the exercise. Determine the DC and AC load line endpoints and also find the maximum peak-to-peak output voltage. This particular exercise, I am only going to show you the answers. I am not going to ask you to solve, because this is a new concept and you may not be able to remember all the formulae right now. That is why I will not be asking you to solve this, but just go through the steps which I am going to show you. It is telling determine the DC and AC load line endpoints and also find the maximum peak-to-peak output voltage. But what I feel is you can solve for DC load line. AC load line endpoints I will show, and the maximum peak-to-peak voltage also I will show. But I hope you can actually plot the DC load line. Can you do it? Now this is the circuit diagram where you can see all the resistors are in ohms. They are not in kilo ohms. You can see that supply voltage is 30 volts and they are not in kilo ohms. Reason is what? We are working with power amplifier. Here the current is in amperes, not in milliamperes. So you can see at the base resistors are in ohms, and even at the collector and emitter resistor are in ohms. There is this load resistance. Now, my dear students, can you quickly tell me the answer for DC load line coordinates? Later on, I will show you the AC load line coordinates. There are 31 students now. At least some of them will put the effort to calculate the DC load line values. That is what I hope, because at least some of them will be actually listening to my lecture. I am waiting for the answer. It should not take this much time actually, because one point is obviously 30 volts in the x-axis. VCC is 30 volts. Other one is 30 divided by 120 plus 20, 30 divided by 140. That is IC SAT. But nobody is giving the answer. You should always have calculator at your hand whenever you come to classes. Because in the second year of Electronics and Communication branch, almost all the theory courses are analytical courses. There is more of a maths content. Anyway, as no one is showing me the answer, let me show you the answer. Okay, Lokesh has given the answer as 0.21 and 30. Harshit has given the answer as 0.214. Okay, let me show you the answer. For the case of DC load line now, VBB is 68 into 30 divided by 490 plus 68 is 3.66 volts. That is the voltage which is found out at the base here. We are finding out the voltage at the base. So that is 68 into 30 divided by 490 plus 68, that is 3.66 volts. Going for the approximate solution here. ICQ is IE is equal to 3.6 minus 0.7, VBB minus 0.7 divided by 20, that is 148 milliampere. When we calculated VBB, actually we had ignored the base current, going for the approximate solution. So ICQ we have found out, that is 148 milliampere. VCEQ is 30 minus same ICQ into that RC, 0.148 into 140, we got 9.28 volts. IC SAT is 30 divided by 140, that is 214 milliampere. So that way the answer which students have given is correct, 0.214 ampere. And Lokesh, your answer is also correct, but at times we cannot leave out the third digit also, or the fourth digit also for that matter, after the decimal point. It is 214 milliampere. As per the answer given by Lokesh, it becomes 210 milliampere. But there is a 4 milliampere difference there, which can become substantial when we calculate the load line. So let us not ignore that way. Let us take it as 214 milliampere only. And VCE cutoff is VCC, it is 30 volts. So these are the two coordinates corresponding to the end of the load line. And we have already calculated the Q point also, ICQ and VCEQ. Now you can see that VCEQ is not at the middle of the load line. It was supposed to be ideally at 15 volts. But we know that in the case of power amplifiers, if the Q is toward the right side, then we have unfaithful amplification. It is better that the Q point is towards the left side. Then we will have a faithful amplification. I have shown you that in the previous slides. So we have obtained the DC load line now. Now let me proceed to show you the solution for AC load line. This is the AC load line. Small RC is 120 in parallel with 180. Why? There is this RL given. You can see 180 parallel with 120. In this case, small R0 is not given. When it is not given, we consider it as infinity or much larger. We directly calculate 120 ohms parallel with 180 ohms. So it is 120 parallel with 180, that is 72 ohms. Now IC SAT and VCE cutoff, applying the AC load lines equations as I showed you here. Here, IC SAT is ICQ plus VCEQ by RC, and VCE cutoff is VCEQ plus ICQ into RC. Now using these two formulae, and later on I am going to use this formula also. Maximum peak output is ICQ into RC or VCEQ, whichever is smaller. So that way IC sat is 0.148 plus 9.28 divided by 72, that is 277 milliampere. VCEQ divided by RC. VCEQ is 9.28 volts. RC is, small RC is 72, as we have already found out here. And this 0.148 is what? ICQ. So accordingly we get IC sat for the AC load line is 277 milliampere. You can see the difference here. In the case of DC load line, it is 214 milliamperes. In the case of AC load line, it is 277 milliamperes. That means there is an increase in the current. And VCE cutoff is 9.28 VCEQ plus 0.148 into 72. That is IC sat into small rc. So VCEQ plus IC sat into small rc. That is 9.28 plus 10.66 is 19.94 volts. Now you can see in the case of DC load line, VCE cutoff was 30 volts, whereas in the case of AC load line, the VCE cutoff came to around 20 volts. 19.94 volts can be taken as approximately 20 volts. That means the current got increased and the voltage got reduced as far as AC load line is concerned. But the Q point is going to be the same there, 9.28 volts and 148 milliampere. Now we can see here VCE cutoff is 19.94 volts, or let us say it is 20 volts approximately. Here you can see VCEQ is at around 9 volts. Now 9 volts to 20 volts, around 11 volts can be the swing there. Later on, let me show you the calculation accurately as per the formula. But now you can predict it. See, Q point is at 9.28 volts. Whereas in AC load line, the VCE cutoff is at around 20 volts. So approximately 20 minus 9 is 11 volts. 11 volts is maximum peak. So maximum peak to peak can be 22 volts. Even though the supply voltage is 30 volts, the peak to peak output which we obtain from this circuit can be only 22 volts. For that reason only we calculate the AC load line. Even when you practically do this circuit as a lab experiment also, you can verify this answer later on. So now maximum peak is 9.28 volts and maximum peak to peak is 2 into 9.28, that is 18.56 volts. So there was this ICQ into RC and VCEQ, right? I'll show you that. Maximum peak can be ICQ into small rc or VCEQ, whichever is smaller. Whichever is smaller. Now because of this AC load line. Let us see that now. Here in this case, even though I told you it is approximately 22 volts, actually we are getting lesser. Why? Here you can see 9.28 ICQ into RC or VCEQ, whichever is smaller. Now when we calculate ICQ into RC is here 0.148 into 72, that is here 10.66. See, there is this 10.66. Let me change the color. There is this 10.66 which is corresponding to ICQ into RC, and there is this VCEQ, right? Out of these, which one is smaller? 9.28 is smaller. Actually, we can find it out from this equation only, instead of, because there are both terms here itself. Out of these, 9.28 is lesser than 10.66. So whichever is lesser, that is considered here. And we are getting around 18.5 volts. Even though earlier I told you it has to be approximately 22 volts. It is not the case that way, because in such a case there can be unfaithful amplification at the other side of the waveform. Fine. Let me proceed now. So MPP is what? 2 into MP. And MP is what? ICQ into RC or VCEQ, whichever is lesser. That is what we have shown here as these values. So this was the solution to the previous exercise. Let me proceed now. Another exercise. Now you can see in the previous slide I showed you some funny pictures where people are trying to reduce the weight. Now this is a very safe method of exercise, practicing yoga here. And you can see at the left side, when person is practicing yoga, even his pet dog is practicing yoga. And the right side is still more cute. In the right side you can see when the person dad is practicing yoga, even the child is practicing yoga. It is very good if you keep practicing yoga right from the childhood, then you will keep your body flexible and fit. Otherwise, in general, what happens is with aging, body becomes more and more rigid, more and more tough, and more stubborn. I keep saying in my other classes that easeful body and peaceful mind will be useful. So body should be easeful, mind should be peaceful, life will be useful. For that matter, if mind has to be peaceful, you will have to practice meditation. If body has to be easeful, you will have to practice yogasanas. In fact, yoga abhyasa is clinically proved. Yoga abhyasa is proved in many other ways to enhance the individual health. Even the social health also, for that matter. If everybody is involved in trying to remain physically and mentally healthy. So that way you can see when the dad is practicing yoga abhyasa, yogasana, even the child is practicing yogasana. This is a good way in the early morning itself. If you dedicate at least a half an hour time daily for such exercises, you will become a fit individual physically as well as mentally. You will become a good adult and you can be a good contributor to the overall health of the society as such. So that is my message for today's class. Once in a while, I keep giving such messages because the teacher's job is to have a holistic teaching, not just the technical teaching. In fact, after you finish your graduation, I want all of you to be very mature, very healthy, very good individuals or engineers who are going to help the society to evolve further and to live better. That is the role of a teacher also. That is why at times I keep giving such tips also. Now, let me show you the next exercise of our class. Determine the DC and AC load line endpoints and also find the maximum peak-to-peak output voltage for the emitter follower power amplifier. In the previous exercise, I showed you one common emitter amplifier. Now, we are going to work out with the emitter follower amplifier. This is the emitter follower amplifier where you can see the supply voltage is 12 volts and you can see at the input it is 50 ohms and 100 ohms, and then at the output emitter resistance is 16 ohms and the load is also 16 ohms. The capacitor values are not given because they are not actually required. Fine. Now let me show you the answer for the emitter follower. Solution is DC load line is VBB is 100 into 12 by 50 plus 100. That is that R1 and R2 are together. So we get the base voltage 8 volts. ICQ is nothing but IE now. It is base voltage is 8 volts minus 0.7 divided by there is 16 ohms there at the emitter. So the quiescent current is 456 milliampere. And VCEQ is 12 minus 0.456, that is ICQ, into 16 ohms IE because collector is connected to the supply voltage directly. So VCEQ is 4.7 volts. Now finally IC sat is what for plotting the load line? 12 volts divided by 16 ohms, assuming the transistor is in the saturation region, that is 750 milliampere. And VC cutoff is what? VCC itself, that is 12 volts. Now proceeding to the AC load line. AC load line, small RE now, it is not small RC because we are taking output at the emitter. there are two resistors